Alright, so today's lesson is about centripetal force. Centripetal force basically means the force that makes something go towards the middle. Okay, so we are talking about a circular movement. We are talking about circular movement and a force that makes it want to go towards the middle of the circle. So if we had a rock attached to a rope and we're spinning that rope around, the rock actually wants to go in that direction as you spin it. Because if we spun it and then cut the line, the rock would just fly straight forward, right? So there is a force that makes it go, oh no, no, keep turning, keep turning. This is called centripetal force. Center towards center force, right? It's a force that wants to make it go towards the center. Same thing as in a car, right? If you're in a car and a car's driving down the road, you're fine, you're in a car. But if the car wants to make the turn, the car actually exerts a centripetal force towards the center. Whereas if I'm sitting inside the car and the car starts turning, I feel like my body wants to go that way, right? Because I want to maintain that motion. Remember Newton's law, where if an object will continue in its motion unless an external force is placed upon it to make it turn. So that external force is centripetal force. So that is the force that allows an object to make the turn, right? We can use common sense to say, well, that rock's going to turn because that rope doesn't change length. It always stays the same. If it's 1 meter rope, it's going to be 1 meter. The rock can't get further away from us, right? But in physics, we have to come up with a rule. What force is allowing it to turn if we know that an object wants to continue straight unless a different force is placed upon it? So we come up with centripetal force. All right? Okay. So if we do a quick little example. Actually, I should give you the equation first. So centripetal force equation is equal to mass times velocity squared over radius. So we know that mass, m is the mass, and it is measured in kilograms, like always. Well, v is the velocity, and it is measured in meters per second, as always. And then radius is r is radius, and it is measured in meters, right? So if we have an example where it says, a father spins his daughter around him while holding her by the hands. The center of gravity of 35-kilogram girl is located 1.15 meters from her father's body. So here's the dad holding hands with the girl, and he's spinning her around. Okay, her mass is 35 kilograms. The radius is 1.15 meters. And it goes on to say, what velocity does little girl have of spinning if her father exerts a force of 700 newtons? So there's a 700 Newton centripetal force pulling in towards him to keep her in place instead of sending her across the yard, right? So we have 700 is equal to 35 times times velocity squared over 1.15. Let's fix that. Whoa, that's a big eraser. 35 times velocity squared over 1.15. And we do the calculation and we get velocity is equal to 4.8 meters per second. Okay, does that make sense? So all it is simple, plug in the numbers and then go from there. All right, next page. Now, remember when we talked about the different forces? If we had a box on a table, we know that there is a force of gravity pulling down on that. And at the same time, the table is exerting a normal force to keep the box in place, right? And therefore, the resultant force is equal to 0. So how does that work if we're talking about spinning an object around now? Let's say you're on a roller coaster. When you are on the bottom of the roller coaster, it's pretty obvious. F, G, and Fn are balanced. So therefore, you don't fall out of the roller coaster onto the floor and hurt yourself. So what if you spin around and now you are at the top Obviously, it doesn't stop there, because if it stopped there, you fall down. It's continuous. But at the very top of the roller coaster, force of gravity is still pulling you down this way. Now, where is the not normal force? Well, now this is the surface. Remember, we are now sitting in that chair. So the normal force is now also pulling down on it. So what is it that keeps us in the chair and not falling down to our deaths? Well, that would be centripetal force. That is going that way. Now, centripetal force also exists at the bottom too, right? Because if we're talking about in a circle, if it's continuous movement, there is still a force, centripetal force, at the bottom. So how is it different from top and bottom? Well, at the bottom you should feel a lot less to be able to. So at the bottom, that is equal to that. At the top, it is equal to double what you feel. So it is equal to that, because you have to balance off both of those. Whereas here, you don't have to balance anything. They're in balance. They're supporting each other. All right. So that should be that. Okay. So as you go through, if it is a vertical from bottom to top, you will have quite a difference in centripetal force. Whereas if you're spinning it above your head, then it's always the same, going around and around and around, because it is not coming towards the ground and away from the ground. Whereas this is coming towards the ground and away from the ground, towards the ground and away from the ground. So therefore, at the top, you need a lot more centripetal force to keep people in the seats than you do at the bottom. Okay, that is all.